Okay, I'm doing things slightly out of order from the book here. We're next going to cover section 4.6, which are limits at infinity. Different from what we talked about before. These are not infinite limits necessarily. These are horizontal asymptotes or end behavior. Remember in college algebra and in pre-calculus, when you did horizontal asymptotes for rational functions and you did end behavior for polynomials. That's what we're talking about here. So we're going to write stuff that looks like this: the limit as x goes to infinity. And we mean as x gets bigger and bigger and bigger, are your y values approaching something? And for this particular graph here, we can just see from the graph, as the x's are getting bigger and bigger, my y values are asymptotically approaching 2. As x approaches negative infinity. So if I'm going backwards on the graph, what are these y values going toward? Also 2. Why does that happen? Because 1 over x there goes to 0. And so you get something that goes like 2 plus 0. Okay, so you can pause at some point and write all this down so you have it in your notes. But that's what we're talking about, horizontal asymptotes. And the key you want to remember is what we call dominating behavior. Anytime you have a fraction, you want to look at the numerator and the denominator and see who's going to win a race. If the top wins, then your limit at infinity is going to be some kind of infinity. If the bottom wins, then that particular part of the function will go to 0. And if it's a tie, then it's ratio of leading coefficients. You remember that, I hope, from college algebra. So I don't need to graph all these guys. We can just think about them. 2 over x squared. Forget about the 5 for a minute. As x gets bigger and bigger, I'm dividing by bigger numbers squared. 2 just stays constant. This part right here is going to go to 0. 5 minus 0 is going to get closer and closer to 5. This limit is getting closer and closer to 5. What about here? Sine of x is always between -1 and 1. The bottom is getting bigger and bigger. If I plug in a billion, sine of a billion is no bigger than 1. 1 over a billion is tiny. The bottom is dominating here. This whole thing is going to go to 0. Arctangent. You should remember the graph of arctangent. I'm in Microsoft Word here, so I can't draw, but think about the graph of arctangent. Think about what happens when x goes to infinity. This graph approaches pi over 2. When x goes to negative infinity, it's negative pi over 2. Okay, what about with polynomials? Like, remember all that stuff you did with the arms in college algebra and pre-calc? The end behavior? That's what we're talking about here. So think about x cubed. As x goes to positive infinity, this arm keeps going up toward positive infinity. If I go backwards on the graph, if I'm writing down, as x goes to negative infinity, this arm goes down toward negative infinity. Now, remember, these limits don't really exist. Anytime you have infinities involved, they're not true limits. That's not really a equal sign. We're kind of lying when we write these, but we're still expressing information. We're still telling somebody this is the behavior. So we're still going to write it. Don't write does not exist here. And then, like, this is all stuff you should remember. then anytime, all right, in here, you have a rational function, maybe something like 8x to the 7th plus 3x minus 2 over 5x to the 7th plus 9x squared plus 100,000. And I want the limit as x approaches infinity of f of x. I'm asking for the horizontal asymptote. I'm asking for the end behavior. Well, with rational functions, there are those three different cases. If the bottom's bigger in degree, the answer is 0. If the top's bigger in degree, then you got either infinity or negative infinity, and you got to look at the graph. But if the degrees are the same, like here, 7th degree, then the answer is the ratio of leading coefficients. So this limit would just be 8 over 5. Oh, but what about that 100,000? Couldn't care less. If I plug in something like x equals a trillion to the 7th power is so much bigger than this guy. Now, why we care about all this is we're going to be looking later at limits of weird looking functions. And what we care about is dominating behaviors. I'm giving you a preview here. What if I wanted the limit as x goes to infinity of e to the x plus 3 over x squared minus 2? Well, both top and bottom want to shoot off to infinity. If I were to plug in infinity into the top, this thing's getting bigger and bigger. So is the bottom. The question is, who wins? Exponentials will beat any kind of polynomial, which will beat any kind of log function. So when it comes to dominating behavior, exponentials win. This limit, that top is going to infinity much faster than the bottom is. This limit will be infinity. If you have an exponential in the bottom, if I have, say, limit as x approaches infinity of x to the 400th power plus 1 billion, or however many zeros I wrote there, x cubed over 2 to the x minus 1. You might think, oh, that's a pretty big power of x. Oh, look at that big giant number. None of that matters. Any exponential is going to dominate any polynomial. The bottom's going to win. If the bottom wins, the answer is 0. If you were to graph this on your calculator and plug in really gigantic values of x, your calculator is going to spit out 0 because the bottom is going to be so much bigger than the top. Okay, it's a good place to stop there.